The responsible workflow is therefore clear. State whether the target is explanation, causal inference, or prediction. Build every candidate model using information genuinely available at the forecast date. Tune complexity within the training data, preserve a final evaluation sample, and compare against simple benchmarks. Then, describe what the evidence supports and what it does not. The next lesson develops regularized regression as one concrete implementation of these principles. In the last lesson, I promised a concrete way to trade a little bias for a lot of stability. Regularized regression is that method. It keeps the familiar regression idea, but changes the fitting criterion. Ordinary least squares picks the coefficients that minimize the sum of squared residuals. When the predictors are many or highly correlated, that unrestricted solution can be unstable. So we add a penalty on coefficient complexity, accepting some bias in return for lower variance and often better predictions on new data. Suppose the outcome at time t equals the inner product of a predictor vector and a coefficient vector, plus an error. If the number of predictors is small and the design matrix has full rank, ordinary least squares is well defined. When the predictor count approaches the sample size, small data changes can produce large coefficient changes. When predictors outnumber observations, many coefficient vectors may fit the training data equally well. The general penalized criterion combines average squared prediction errors with lambda times a penalty on the coefficient vector. Lambda is a non-negative tuning parameter. When lambda is 0, we recover ordinary least squares. As lambda increases, the penalty has greater influence, and the fitted model becomes less flexible. The useful value of lambda is an empirical question that should be answered with validation data rather than training fit. Ridge regression uses the sum of squared coefficients as its penalty. Its solution shrinks every slope towards 0 and remains unique even when predictors outnumber observations, provided the penalty is positive. Ridge is particularly helpful when several predictors carry similar information. Instead of assigning a large positive coefficient to one and a large negative coefficient to another, it distributes the signal more smoothly and stabilizes the combined prediction. Ridge generally does not set coefficients exactly to 0. That property can be an advantage when the signal is dense, meaning that many predictors each contribute a small amount. It can be a disadvantage when a compact selected model is important. The method should therefore be described as shrinkage, not automatic variable selection. A small ridge coefficient is still part of the prediction rule. The lasso uses the sum of absolute coefficient values as its penalty. The corner shape of this penalty allows some estimated slopes to become exactly 0. Lasso therefore combines shrinkage with variable selection. As lambda rises, the active model usually becomes smaller. This sparsity is attractive when we believe that only a limited subset of many candidate predictors carries useful incremental information. In a simple orthogonal setting, the lasso follows a soft threshold rule. If an unregularized signal is smaller in absolute value than the threshold, its estimate becomes 0. If it exceeds the threshold, the estimate keeps its sign, but is pulled towards 0 by the threshold amount. This example explains both the selection benefit and the shrinkage bias that Lasso can impose on genuinely large coefficients. Correlated predictors complicate variable selection. Lasso may choose one member of a highly correlated group and discard the others, and a small change in the sample may change which member is selected. Ridge tends to share weight across the group. Neither behavior is automatically correct. Selection stability, predictive loss, and the substantive meaning of the variables should all be examined before giving a selected coefficient an economic interpretation.